So I'm a PhD student in ocean and coastal engineering and technically civil engineering. And I wanted to make some videos just kind of like talking about my experiences in a PhD program and uh, just kind of like as a kind of like a journal to record my progress. Um, yeah, so I got this whiteboard. I'm in my room right now actually because I got this whiteboard during COVID, and that's actually when I started grad school. I was thinking, we're going to be in lockdown, and what's more useful than having a whiteboard at your disposal? And yeah, so here I am at the whiteboard in my room, and yeah, so I study basically the physics of, maybe it'd be better to say the mathematics of waves, specifically ocean waves, but the mathematics is pretty broad, so the equations that I study apply to various systems. And at my university, we're focused on the research into wave energy converters. And so what that really means is that what we're looking at is a fluid and structure interaction problem. And where I come into that is I look at the wave field and I want to characterize what's happening as the waves are hitting the wave energy converter. And obviously we want to know things like how fast is the water moving, or how much force is that applying on the wave energy converter, how much energy is in the wave and at what frequencies. Because if we know that, then we can control our WEC. Wave energy converter is usually shortened as WEC, and we can harvest energy more effectively. And that turns out to be a very complicated problem, and there's a lot that goes into that, like an understanding of statistics, measurement, physics of waves, and it's a very interesting problem, and there's a lot of depth to it. But yeah, right now I'm just finishing up my term. It's almost June. I got a couple more weeks left. This term I'm taking complex analysis and ocean structural dynamics. So let's see, complex analysis. It's a pure math class. So we also at my university have a complex variables class, which is like the applied version. Like, what is a complex number? How do we integrate? How do we represent complex numbers in different ways? And then complex analysis is sort of more pure math approach to those kinds of concepts, like the residue theorem and holomorphicity and meromorphicity and singularities and types of singularities, calculating residues, and even though it's a pure math class, it tends to be more on the applied side. And ocean structural dynamics is, it's exactly what it sounds like. This class is taught by my advisor, and it's really about how, when we place a structure in the water, how do we determine the forces that are acting on it, and how do we characterize the waves and their reaction to this object that has been placed in the water. And there are a lot of various assumptions that you have to make, simplifications in the way that you solve the problem If anyone has experience with like computational or numerical mathematics, you sort of like solve one. It's like a series of problems, and you solve one at a certain time step, and then that allows you to solve the next one, and that's sort of the coupling of the problems, and you know you solve the problem as if it was just the fluid propagating forward, just the waves moving, and then you place the structure there and act as if it couldn't move, and then you solve the problem. Just 1 second. I have a fan that comes on automatically, and it just happened to come on right now. So you solve the problem as if the structure was there and it couldn't move, and then that gives you the forces on the structure, and then you allow the structure to move, and you solve it again, and you sort of a single step in time, and then you get all these. That allows you to produce the solution for the next time step, for the wave field at the next time step, and then you repeat the process over and over again. But there are all these considerations to make, like when a structure moves in fluid. Maybe I should draw something here. So if I have some sort of like submarine looking thing, if this is moving, so we're submerged in the water, and if this is moving forward, there's all this fluid here that has to be pushed out of the way. So there's what's called the added mass term, and you have to determine how much mass is added. In your equation of motion, you have F equals ma, but really in a dense fluid, there's some sort of mass added to the mass of your object that you have to also push out of the way in order to move. And I mean that's true in air. You have to push mass out of the way, but air is so not dense that we just neglect that term. And anyway, what I've been doing, my free time recently, what I've been doing is I've been starting to go through this book. I just want to spend some, because in the summer, it's almost the summer, and in the summer it's mostly we focus on research, and I want to spend some time, now that I've had been in grad school for 4 years now, I want to spend some time reviewing some of the foundational concepts again, just with a different mindset. And so I've been looking at the physics of vibrations and waves, sort of an introductory textbook. Well, it starts at the introductory level, and it covers quite a bit of ground. So first chapter is simple harmonic motion. Chapter 2, you add damping to that, so something that is slowing down the motion. The forced oscillator, so you add forcing terms. In our wave problems, the forcing is the wind. So we have wind blowing on the water, and that forces it, and then at some time the wind stops, the waves move downstream, so to speak. It's the ocean, so it's not really downstream, but and we call that like a fully developed sea, is when the wind has pushed the waves. It's sort of, the motion has been fully developed, and then they're kind of traveling. Coupled oscillations, then transverse wave motion, longitudinal waves, waves on transmission lines, electromagnetic waves, waves in more than one dimension, Fourier methods. So Fourier methods are something we use every day because the wave field is a composition of, it's a composition of waves. We applied the principle of linear superposition to, we take a wave, the waveform as it's measured in the field, and we transform it, and we get we get all these different frequency components, and obviously that allows us to decompose the wave into various simple oscillators, basically. And like waves in optical systems, interference and diffraction, wave mechanics, nonlinear oscillations in chaos, nonlinear waves, shocks and solitons. So that's where my research is, in nonlinear waves. It turns out that the principle of linear superposition, what you really need to satisfy that is that the different components of the wave are non-interacting. In that way you can just sum them. You can sum a series of sines, let's say, and that actually turns out to be the case only under certain conditions. So if the wave amplitude is small, then the interactions between the waves that are actually present are small, and so summing them leads to a very small error. But as waves become more energetic and steep and tall, that assumption kind of breaks down, and that's really the focus of my research. But yeah, I hope to go through some parts of this. I've taken classes on like structural dynamics before, which is really all about simple harmonic motion, damped simple harmonic motion, forcing an oscillator. But really just reviewing it, because seeing it once is really not enough to make you an expert on anything. So yeah, maybe I could talk about just some of the basics here. So why don't we go through, let's do a pendulum. So classic setup is that we have a rod, an infinitely stiff rod of length L, swinging, making an angle of theta. And really the way we think about all of these problems is sort of like spring mass systems. So we know that so if we have a spring and a mass, there's some position this system naturally rests at, and we call that the sort of the x naught. We would just call that 0. And we know that the spring is stiff, and so if we bring this out to, say, x1 here, and we extend that spring, because this would be x1 minus x naught, then there's going to be some sort of restoring force on this mass, and that's due to the stiffness of the spring. And we can characterize all of these simple harmonic motion problems in this same way, and what we really want to do in this setup here is sort of determine what the stiffness is. And in this way, so we see that the force of the stiffness, the force that the stiffness is applying, the spring is applying, rather, is proportional to, so again, force is directional, and if we displace this, we see that the force of the spring is in the opposite direction of the displacement. So if we consider that displacement being positive, then this force is acting in the opposite direction. So the force is proportional to some stiffness and the distance that we've displaced it. And we just assume that the stiffness is constant, meaning that no matter how far we go out, the stiffness is not going to get bigger as the displacement gets larger. And that turns out to be a really good approximation if the displacement is small. And that's really sort of the core of what's going on, is that we have this small displacement and constant stiffness. So what's going on here? Well, if we think of stiffness is force, restoring force per unit distance, right? And here the restoring force is gravity. And the gravity is acting on this mass here. And so our force is mg. And we need to know what distance this is. Well, we can say it's theta, but we really want, at least at this point in time, we want the distance just in terms of x, our x coordinate here. And, well, I guess what we can say, really to connect the angle and x here, is we can say that L sine theta is equal to x. L sine theta is equal to x, and that just tells us that x over L is equal to sine theta. So really our distance here is x over L. So this is negative, and then we apply Newton's second law, force equals ma, classic. So this is our force, and this is equal to mass times acceleration. And of course, acceleration here is just the second derivative of the position. And so we sort of bring this all to one side, and we get and so our stiffness in this, so in our spring example, the stiffness is the spring stiffness, the spring constant, K. And here we see that the stiffness is mg over L. And what we can do is sort of transform this into a canonical representation. And so what we would do is we can divide out the mass, g over L, x equals 0. And what we do is we set this to omega squared. So we say g over L equals omega squared. Because, and this comes with experience, we know that the solution to this is, this is going to be oscillatory. And so the solution to this is going to be sines and cosines. And so we want this constant term here to be the frequency of vibration. And so what we do is we kind of reduce the frequency of vibration depends on the stiffness, is really what I'm getting at. And so in all of these systems we can sort of reduce down to this canonical form. And I haven't even written it yet, but depending on the system, the stiffness is going to change, and so of course the frequency is going to change because the frequency is dependent on the stiffness. And that's a really fundamental fact about things that oscillate. Maybe I could just solve it really quickly. And I mean, solving it, really, we could produce what's called the characteristic polynomial by substituting maybe we'd substitute like a E, not E, X. I omega t, something like this. And we could get the what's called the characteristic polynomial, and that would allow us to produce eigenvalues and eigenvectors. But really what most textbooks do, and what this one does, at least at the start, is sort of just says, well, x, let's just guess the solution because we expect it to be of this form. And it's not very illuminating, but it gets you to looking at results much faster, which is nice because then you build up some intuition for the system. And really the approach to the solution is really a mathematical it's a mathematics, really. And that's useful, obviously. I mean, I take a lot of math classes, so I think it's very useful, but we don't want the math to get in the way of learning the physics. Anyway, so a cosine omega t plus b sine omega t. And if you know the Euler's formula for a complex number, you'll see that this is very reminiscent of that, though it's not quite that. So we have, anyway, so our equation, x double dot plus omega squared x equals 0. To see that this is a solution, obviously we need to take the derivatives. Okay, so here's our derivatives, and we look at the form of the equation and we say, well, that the second derivative here should equal negative omega squared plus x, because they have to sum to 0, so this has to be negative omega squared x. So if we multiply this top one by omega squared, so omega squared x, negative, not negative, and we can just see right here that they are indeed opposite. And so we have our form of the solution, and like I said, it's nice to get the canonical form for the problem, because then if you can reduce your simple harmonic motion down to this form with some different form of omega squared, so different stiffness, then you have the form of the solution already, and you don't really need to get pay close attention to how your the form of your stiffness. You can just write it in omega squared, and that's really the right way to think about the problem, because we're really looking at frequencies of vibration, and that comes in handy when you have the superposition of many oscillations at different frequencies, and characterizing that, you want to think of it all in terms of frequency and not in terms of some stiffness. Yeah, so I think that's everything.